Welcome back to Think Design Works Smart. I'm Alex Bolboaca and I'm coming at you from the Mozaic Works studios. And what I have for you today is the reaction to an article by Herb Sutter called C++ Safety in Context. This comes in the context of the discussions we were having. So 1 year ago, NSA recommended the usage of memory-safe programming languages for new software products, and the switch to memory-safe programming languages as a way to reduce potential security breaches. And later on, 1 year later, on I think it was 27th or 28th of February this year, the White House has published a press release that recommended the usage of memory-safe languages, and those memory-safe languages excluded C and C++. And so this is the first deep analysis that I've read regarding the actual C++ problems, and I find it very, very interesting and insightful, and this is why I believe it's useful to look at it. Even if you are not a C++ programmer, security issues will grow up on us. So we need to be more in line with what is happening in terms of security, because you will need to know more and more about security in the next years, given everything that's happening, state actors attacking various institutions. Hey, only last week, French institutions were attacked by some hackers, and they haven't, or I haven't seen an update on that, but it's most likely some state actor. So we need to be more prepared for these types of issues. And so this is very informative. Herb Sutter, as usual, is giving a very good analysis of all these, this topic. And this topic has inflamed a lot the C++ community. You could see in the comments on our previous videos on that, we had people posting things like, yeah, there is no such thing as a memory-safe language, or yeah, it's a conspiracy, you know, Microsoft and Google want to take over, things like that. And look, what we need to do is to do a real analysis and to look at the challenges that C++ has and at where there are no problems. And basically this is what Herb Sutter is doing, and I really like his approach. So I'm gonna skip, you will have the link in the description. I'm just gonna point out some of the important parts of this article. And it starts by stating the real issue. We must make our software infrastructure more secure against the rising cyber attacks, such as on power grids, hospitals, and banks, and safer against accidental failures with the increased use of software in life-critical systems, such as autonomous vehicles and autonomous weapons. The past 2 years in particular have seen extra attention on programming language safety as a way to help build more secure and safe software, on the real benefits of memory-safe languages, MSLs, and that C and C++ language safety needs to improve. I agree. And that's basically what I was saying in the past. There are known issues with C and C++ safety, but I'm going to focus on C++ mostly. But there have been misconceptions too, including focusing too narrowly on programming language safety as our industry primary security and safety problem. It isn't. Many of the most damaging recent security breaches happen to code written in memory-safe languages. For example, the Log4j security issue that was, I think, 1 year ago, or had nothing to do with programming languages. Kubernetes secrets stored on public GitHub repos. Yeah, this is a very well-known issue. Stop storing secrets publicly because, it's a bit of a problem. So a quick hint here. If you are afraid you're ever going to store secrets publicly, create in every repo a folder secrets and make it a habit to add in your gitignore file /secrets. And then with good habits, you can be safer. It doesn't mean that you won't be able to still leak some secrets, but at least if you use this habit for every piece of software that you do, it's easier to avoid the issues. It's less likely you'll have this issue. Okay, so I agree with this. Programming language safety is not the only issue, and there are many others. However, this doesn't mean that it's not an issue that needs to be solved. And to me, I think knowing how governance works, I think what NSA and the White House have tried to do is to figure out what is the first thing that we can do to reduce and improve security. And I really hope that they are looking beyond that, because if they stop here, it's not enough. But this is one that can be addressed faster. So it's more like a low-hanging fruit. Now, it cannot be addressed very fast, but it can be addressed faster. Knowing everything that happens in security, this is actually a big thing. And it's also easier to kind of manage. It's easier to know when you have solved these things, or when you have improved on memory safety compared to other things. So, having something measurable is always better. In that context, I'll focus on C++ and try to highlight what needs attention, what C++ problem is, and how we can get there by building on solutions already underway, address some common misconceptions, what C++ problem isn't, including practical consideration of memory safe language, and leave a call for action for programmers using all languages. And the brief is, I don't want C++ to limit what I can express efficiently. I just want C++ to let me inform our already well-known safety rules and best practices by default, and make me opt out explicitly is that's what I want. Then I can still use fully modern C++, just nicer. And this is basically what I was saying with, I think from the first time the NSA talked about memory safe languages. What we need for C++ is a profile that is more secure by default. And then, okay, if you're doing device drivers or whatever things where you need to do more memory management in weird ways and pointer arithmetic or whatever you're doing, then absolutely. You should be able to do that, but that's a different profile than people who develop applications. And we should just take it as we should just embrace this fact of life, that writing device drivers or firmware or things like this, it's a very different type of software than applications that run on desktop computers or that run on servers. So the immediate problem is that it's too easy by default to write security and safety vulnerabilities in C++ that would have been caught by stricter enforcement of no rules for type, bounds, initialization, and lifetime language safety. So we know that there are some issues, types, bounds, going out of bounds. And you have here some examples. So out of bounds write is when you allocate memory, but then you can write outside the allocated memory. Out of bounds read is when you can read memory outside the allocated one. Use after free, you have allocated memory, freed it, but then you still use the same memory. And this is particularly bad if you have secrets in memory. Like imagine you have passwords or things like that. And somebody is able to use after free, so basically to access the memory area that was freed but that was not cleared. And this means that they can read the secrets. That's a bit of a problem. But not only, right? It can be used for a bunch of different things. Null pointer dereference, right? You have a null pointer, you dereference, and the system blows up. And yeah, so basically what Sutter is saying is that you need type bounds, initialization, and lifetime language safety. And these are known problems. They are well documented in the C++ literature. It's just that it's hard, or they need discipline to be implemented correctly and in order to avoid these types of issues, right? And enforced. In C++, we need to start with improving these four categories. These are the main four sources of improvement provided by all the memory safety languages that NIST, NSA, CISA, etc. recommend using instead of C++. So by definition, addressing these four would address the immediate NIST, NSA, CISA issues with C++. And in all recent years, including 2023, these four constitute the bulk of those oft-quoted 70% of common security vulnerabilities and exposures related to language memory and safety. However, that 70% of language memory and safety CVEs is misleading. For example, most of 2023's most dangerous weaknesses did not involve language safety and so are outside the denominator. More on this under the problem isn't. Yeah, so of course there are some misconceptions, and it's really great to see that Sutter is clearing that map, but they don't absolve us from actually doing the right thing and writing code that is safe by default. And this problem is even enhanced in C++ by the huge amount of existing code that could be written using these could have these issues. The C++ guidance literature already broadly agrees on safety rules in those categories. C++ should provide a way to enforce them by default and require explicit opt-out when needed. We can and do write good code and secure applications in C++, but it's easy even for experienced C++ developers to accidentally write bad code and security vulnerabilities that C++ silently accepts. And that would be rejected as safety violations in other languages. We need a standard language to help more by enforcing the known best practices rather than relying on additional non-standard tools to recommend them. Yeah. So basically the way you can do this in C++ is if you write code and then you either have some manual checks like code reviews and discipline checks. Pair programming, mob programming would be good ways of dealing with these issues. But In addition to that, you can use various types of tools. However, those tools are non-standard, and you have to pick tools that match your context, and sometimes, maybe they are tools that require licenses, maybe they are, and you don't have the budget for those, and so on. So this is not an easy problem. Even if we have tools that are not standard, probably you need to know how to configure them. Based on my experience with static analysis tools, they would give us, like, for existing code bases, I often would get like thousands of issues reported, and I just had to configure them to select just the most important ones first, so that to clear those up. Otherwise, we would be just flooded by issues reported by static tools, and you cannot stop development just to fix issues reported by static tools. Also, sometimes the issues were not relevant or incorrect. So these are not the only 4 aspects of language safety we should address. They are just the immediate ones, a set of clear low-hanging fruit where there is both a clear need and a clear way to improve. Software safety is also important. Cyber attacks are urgent, so it's natural that recent discussions have focused more on security and CVEs first. But as we specify in the default language safety rules, we must also include our stakeholders who care deeply about functional safety issues that are not reflected in the major CVE buckets but are just as harmful to life and property when left in code. Programming language safety helps both software security and software safety. And we should start somewhere, so let's start but not end with the known pain points of security CVEs. So maybe it's useful to discuss a little bit the difference between security and safety. Security refers to protection against outside attacks, various breaches, while safety in this context is more about if you have this software running on a device that it's safe. It actually, the device does not do anything harmful. And the article started with a reference to autonomous vehicles, autonomous weapons, right? You don't want autonomous vehicles to start, to start accelerating and you cannot brake. This would be a really bad thing. And this is a safety issue. It's not a security issue. It's not that somebody hacked into your car and made it accelerate. It's more likely, when it happens, that the software, the controlling software had a bug and accelerated instead of for some reason and didn't allow you to brake. So it's a safety problem, it's not a security problem. It would be a security problem if an external hacker could hack into your car and accelerate it. In those 4 buckets, a 10 to 50 times improvement, 90-98% reduction is sufficient. If there were 90 to 98% fewer C++ type bounds in initialization lifetime vulnerabilities, we wouldn't be having this discussion. All languages have CVEs, C++ just has more. So far in 2024, Rust has 6 CVEs, and C and C++ combined have 61 CVEs. So 0 isn't the goal. Something like a 90% reduction is necessary, and the 98% reduction is sufficient to achieve security parity with the levels of language safety provided by memory-safe languages, and has the strong benefit that I believe it can be achieved with perfect backward link compatibility. That is, without changing C++ object model and its lifetime model, which does not depend on universal tracing garbage collection and is not limited to tree-based data structures, which is essential to our being able to adopt the improvements in existing C++ projects as easily as we can adopt other new editions of C++. After that, we can pursue additional improvements to other buckets such as thread safety and overflow safety. And okay, he's saying that aiming for 100% or zero CVEs would be a mistake because, yeah, it's an overkill and it's very costly. So this is not that. I'm gonna skip that section. A 98% reduction across those 4 categories is achievable in new updated C++ code and partially in existing code. Since at least 2014, Bjarne Strustrup has advocated addressing safety in C++ via subset of a superset. That is, first superset to add essential items not available in C++ 14, then subset to exclude the unsafe constructs that now all have replacement. As of C++ 20, I believe we have achieved a superset, notably by standardizing span, string view concepts, and bounds-aware ranges. We may still want a handful more features, such as null terminating z-string view, but the major additions already exist. Yeah, so you should be using these, particularly the ranges library, which is now part of the standard language. That's very powerful. And it basically takes C++ to the level where you can write in C++ code that is very similar to what you would write in C# and Java, but with better performance, so without sacrificing performance, at the same time with better safety, so parity on memory safety. Now we should subset, enable C++ programmers to enforce best practices around type and memory safety by default in new code and code they can update to conform to the subset. Enabling safety rules by default would not limit the language's power, but would require explicit opt-outs for non-standard practices, thereby reducing inadvertent risks. And it could be evolved over time, which is important because C++ is a living language and adversaries will keep changing their attacks. ISO C++ evolution is already pursuing safety profiles for C++. So this is a big problem indeed, and the problem is that you have a lot of existing code in C++, and how can you fix existing code without actually changing the code? It won't be 100% possible, but by having these good defaults and then having the warnings when you are doing something that's wrong and having to do an opt-out, at least is, I think is the best idea, and that's what I was thinking about initially. We should have different profiles for C++, and look, they are working on safety profiles. So, yeah. Everyone agrees that many safety bugs will require code changes to fix. However, how many safety bugs could be fixed without manual source changes? So then just recompiling existing codes with safety profiles enabled delivers some safety benefits. For example, we could by default inject a call side bounce check 0, so we call them b less than a.size for every subscript expression a of b. When a.size exists and a is a contiguous container without requiring any source code changes and without upgrading to a new internally bounce check container library. That checking would just work out of the box with every contiguous C++ standard container, span, string view, and third-party custom container with no library updates needed, including therefore also no concerns about ABI breakage. So this is really the dream, I think. If you could make these changes work, and even for slightly more complex scenarios, without introducing too many performance issues, because I think this proposal, I mean, I know some C++ programmers will frown on this because if you need to check every time, then this will be slightly slower than it is. And, sometimes these things matter in the C++ world, particularly if you're dealing with under milliseconds. So if you're dealing with microseconds, with picoseconds, it's important. And it might have an effect. On the other hand, we have better processors now, more memory, who knows, maybe it's not such a big deal. Rules like those summarized in the appendix would have prevented at compile time, test time, or runtime most of the past CVs I reviewed in the type bounds and initialization categories, and would have prevented many of the lifetime CVs. I estimate roughly 98% reduction in those categories is achievable in a well-defined and standardized way for C++ to enable safety rules by default and retains perfect backward compatibility. We can and should emphasize adaptability and benefit also for C++ code that cannot easily be changed. I found this very interesting because there are a few things I haven't thought about. There is a lot of C++ code existing, but also there's a lot of C++ code that is very difficult to change. Why? Well, let's see. Any code change to conform to safety rules carries a cost. Worse, not all code can be easily updated to conform to safety rules. For example, it's old and not understood. It belongs to a third party that won't allow updates. It belongs to a shared project that won't take upstream changes and can't easily be forked. That's why I stress that C++ should seriously try to deliver as many of the safety improvements as practical without requiring manual source code changes, notably by automatically making existing code do the right thing when that is clear. For example, the bounce check mentioned above, or emitting static cast pointer downcast as effectively dynamic cast without requiring the code to be changed. And by offering automated fixes that the programmer can choose to apply, example, to change the source for static cast pointer downcast to actually say dynamic cast. Even though in many cases a programmer will need to thoughtfully update code to replace inherently unsafe constructs that can be automatically fixed, I believe for some percentage of cases, we can deliver safety improvements by just recompiling existing code in the safety rules by default mode, and we should try because it's essential to maximizing safety profiles, adaptability, and impact. So I find all these quite interesting, and I think casting is another problem that I haven't discussed. So for example, if you have a pointer of a specific type, and then you cast to another type, and the types have different sizes, that's a common way of having memory issues. And I guess this is what they are saying with static cast and dynamic cast. It's probably a way of dealing with these issues without having to change much. Well, you need to change a word and that's it. The thing here is, particularly one thing that jumps to me is when it belongs to a third party that won't allow updates. I think one of the problems here is also of responsibility, and I believe software companies should be made more responsible for security and safety improvements. If there are some issues in the code, for example, if your library, your framework doesn't work with these memory safe requirements, I believe you should have to change it within a reasonable time frame, but actually invest into updating it. It's no longer just about business, it's also about other things like, safety, security. These this will be more important as time goes by. So typically software companies are not held responsible for much, and I think it's time to start. Okay, well, the problem isn't some common misconceptions. So until now, he talked about the actual problems and how to fix them, and I really like the solutions. They don't address everything, but they do address the most important parts, which is, the different categories of memory safe issues and the way to solve those through standard means, which would be great. The only problem here is that standardization in C++ doesn't take a short time usually. So I'm really curious to see when this will be included in the language. Might take a while, and it might be a bit too late. I hope not. C++ is still a very important language, I think, and I'd like to keep it if it were, if you would ask me. But really it depends on how fast they can include these things in the standard. That would make a big impact. Okay, so what the problem is and some common misconceptions, I'm just gonna skim read through these. The problem isn't defining what we mean by C++ most urgent language safety problem. We know the 4 kinds of safety that most urgently need to be improved: type bounds, initialization, and lifetime safety. We know these 4 have low-hanging fruit. It's true that these are just for perhaps 2 dozen kinds of safety categories, including ones like safe integer arithmetic, but most of the others are either much smaller sources of problems or are primarily important because they contribute to these 4 main categories. For example, integer overflows we care most about are indexes and sizes, which fall under bound safety. Most memory safe languages don't address making this safe by default either, typically due to the checking cost. Yeah, so Microsoft ships a safe-int library for C++ to handle integer overflows, which is opt-in. C# has a checked arithmetic language feature to handle integer overflow, which is opt-in. Python built-in integers are overflow safe by default because they automatically expand. However, the popular NumPy fixed-size integer types do not check for overflow by default and require using check functions, which is opt-in. So there are various other problems. Thread safety is obviously important too, but it is not one of the top target buckets. And actually, yeah, most programming languages don't have, they are comparable with C++, thread safety. The problem isn't that C++ code is not formally provably safe. Yeah, and I think I've seen some comments about that, about formal provability. And this is the common disconnect I see between the computer science university types and the software developer engineering types. And I understand that we have some theories and they are really nice. It's the same with functional programming, right? You have category theory and you have what are the church numerals, and they are really nice as theory, but then you need to implement something that works, scales, is fast, is implemented and ready to use yesterday. You cannot have all the nice theory in practice. So I understand. Formal provability would be really cool, but honestly, it's most likely impossible to do in a real work environment. And I like how he puts it. I've seen some people claim we need to require languages to be formally provably safe, and that would be a bridge too far. Much to the chagrin of computer science theorists, mainstream commercial programming languages aren't formally provably safe. Yeah. And for example, none of the widely used languages we view of memory-safe languages except uniquely Rust claim to be thread-safe and race-free by construction, yet we still call C#, Go, Java, Python, and similar languages safe. Therefore, formally guaranteeing thread safety properties can be a requirement to be considered a sufficiently safe language. It's basically the de facto standard, right? We have a level of safety that we can reasonably achieve. And maybe we could go a little bit over that, but usually when we try to go all the way to implement the computer science theories, things start to get either very slow in production or very slow in development, and neither of these is a good way of or an improvement. Okay, that's because a language choice of safety guarantees is a trade-off. For example, in Rust, safe code uses tree-based dynamic data structure only. This feature lets Rust deliver stronger thread safety guarantees than other safe languages because it can more easily reason about and control aliasing. However, this same feature also requires Rust programs to use unsafe code more often to represent common data structures that do not require unsafe code to represent in other memory-safe languages such as C# or Java. And so 30 to 50% of Rust crates use unsafe code compared, for example, to 25% of Java libraries. Yeah, so you see, you always have a trade-off. And I think that's a bit of a problem. And I also found this interesting. C#, Java, and other memory-safe languages still have use before initialize and use after destroyed type safety problems too. They guarantee not accessing memory outside its allocated lifetime, but object lifetime is a subset of memory lifetime. Objects are constructed after and destroyed, disposed before the raw memory is allocated and deallocated. Before construction and after dispose, the memory is allocated by contains raw bits that likely don't represent a valid object of a type. Yeah, so this was pretty common. The use after dispose bugs, this is something pretty common because in C#, if I remember correctly, there was a disposable. So you could implement a disposable function because they take care about memory, but if you have, for example, a open file or open connection to a database or anything else that would create additional things other than memory, you would need to implement this dispose, and then you need to remember to use dispose. Now, granted, there were some language features, so you could say use or using of this object, and that would automatically call dispose when exiting the using block. So it was slightly easier, but it was still possible to dispose and then to use the object, and that is a bug. So all kinds of things, right? And it's true. No programming language can avoid all these problems, or they don't avoid all these problems today, and I don't think they will ever do. But what they can do is to provide reasonable defaults and create habits, things that if you do again and again and again, they just, they work. Okay. The problem isn't that moving the whole C and C++ code to memory-safe languages would eliminate 70% of security vulnerabilities. So that's true. It's not that 70% of programming language cause CVEs reported security vulnerabilities in C and C++ code are due to language safety problems. The number is true and repeatable, but has been badly misinterpreted in the press. No security expert I know believes that if we could have a magic wand and instantly transform all the world's code to MSLs, memory safe languages, that would have 70% fewer CVEs, data breaches, and ransomware attacks. Yeah, absolutely. So there are all kinds of attacks. And there's a whole analysis on why this percentage is not a... So if you say that 70% of the CVEs are related to memory, it doesn't mean that if you remove that, you'll remove 70% of CVEs. And it's all quite clear why. And the article gives a few details here, but I think another one would be that once you solve these types of issues, attackers will try other things. So you'll get 70% of CVEs going into another place. Is the basic 80-20%, only in this case it's 70-30. So let's figure out how to reduce this 70%, but then we'll find another 70% lurking in. It's Pareto all over again. The problem isn't that C++ programmers aren't trying enough using the existing tools well enough. The challenge is making it easier to enable them. Yeah. So I've seen this. You can, like one of the comments I think was, yeah, you can just use sanitizers, static tool, static analysis, various things. That's true. But how easy it is to find the right mix, and how easy it is to set it up in a corporate environment, for example. Do you need a budget? Do you need somebody to install it on a server and include it into your automated build? How fast will you get the reports? All kinds of stuff like that. And in addition to this, there's a whole bunch of things. C++ has been around for a very long time. So we have a bit of a problem with how many of these things are and how varied. And how you pick the tools is not that easy. And I like this list. Today, the mitigations and tools we do have for C++ code are an uneven mix and all are off by default. They are a mix of static tools, dynamic tools, compiler switches, libraries, and language features. Acquisitions, they are required in a mix of ways. In the box in the C++ compiler, optional downloads, third-party products, and some you need to Google around to discover. Accuracy, existing rule sets mix rules with low and high false positives. The latter are effectively unadoptable by programmers, and their presence makes it difficult to just adopt this whole set of rules. Determinism. Some rules, such as ones that rely on interprocedural analysis of full call trees, are inherently non-deterministic because the implementation gives up when fully evaluating a case exceeds the space and time available. This means that two implementations of the identical rule can give different answers for identical code. Cool. So not only you have, it's difficult to find the tool once you implement, you get it, you install it, you include it, it will give mixed results. Nice. Efficiency. Existing rule sets mix rules with low and high and sometimes impossible cost to diagnose. The rules that are not efficient enough to implement in the compiler will always be relegated to optional standalone tools. Portability. Not all rules are supported by all vendors. To address all these points, I think we need the C++ standard to specify a mode of well-agreed and low or zero false positive deterministic rules that are sufficiently low cost to implement in the box at build time. Yeah. And we'll end, it ends with a call to action, which is really cool. I like it. As an industry, generally, we must make a major improvement in programming language memory safety, and we will. In C++ specifically, we should first target the 4 key safety categories that are our perennial empirical attack points: type, bounds, initialization, and lifetime safety, and drive vulnerabilities in these 4 areas down to the noise for new updated C++ code. And we can. But we must also recognize that programming language safety is not a silver bullet to achieve cybersecurity and software safety. It's one battle, not even the biggest in a long war. Whenever we harden one part of our systems and make them more expensive to attack, attackers always switch to the next slowest animal in the herd. Many of 2023's worst data breaches did not involve malware but were caused by inadequately stored credentials, Kubernetes secrets on public GitHub repos, misconfigured servers, lack of testing, automated tests, supply chain vulnerabilities. Do you know where the library is coming from that you're using? Could anyone have changed the library from where you are downloading until you're compiling? Social engineering and other problems that are independent of programming languages. No matter what programming language you use, security hygiene is essential. Do use your language's static analyzers and sanitizers. Do keep all your tools updated. Do secure your software supply chain. Do use package management for library dependencies. Do track a software bill of materials for your projects. By the way, how easy it is today to use, and how many of you who are doing C++ use package managers for C++? Once again, there is no standard, which is a pity. Don't store secrets in code, or for goodness sakes, on GitHub. Yeah, so if you store them on your hard drive, remember this trick. Create a secrets folder and limit access to the minimum you can, and ignore the secrets folder in your git ignore. This makes wonders. Do configure your servers correctly, especially public internet-facing ones. Turn authentication on, change the default password. Do keep non-public data encrypted, but when at rest and when in motion, both when at rest and when in motion. Do keep investing long-term in keeping your threat modeling current so that you can stay adaptive as your adversaries keep trying different attack methods. Yeah. So I really like this. I think this is a very good analysis of the problems and of the things that are not problems. I can see that he got similar responses as I've seen on our past videos on this topic, and addressed them, in a really good way. I like this. And this is basically what we should be doing, not only for C++, but for every other programming language and software product that we are building. Security is becoming more and more of a concern, and I think it's really, really important to make sure that this that we take a lot of care with security. And let me show you something, because I really like this. We have a learning program that's called Secure Coding, and it's been really, really useful for programmers who started doing and who need to start thinking more and more about security. And we start with the fundamentals, basically thinking like an attacker, understanding attackers, and then understanding how to protect against potential attacks. So, yeah, there's a lot of stuff that's useful here, and I think there's a lot more that we can discuss about when it comes to security. But one of the most important things is to have the correct mindset. The mindset is paramount when it comes to security issues. And as a developer, you should always think not only through the lenses of does this work, does it do what it's supposed to do, and is this easy to change, is this design easy to understand and the code easy to read, is performance enough, and so on. But you should also think about how could anyone breach into this code, and what are the small things that I can do to limit the possibility of this happening. Yeah, security is becoming more and more of an important issue, and I'm sure we'll need to learn more about it in the next years. Okay, what do you think about this analysis? Do you agree with Herb Sutter? Is there anything that is missing? Are you facing any problems with existing code bases that you don't know how to fix? Let us know in the comments, and let us know what you think about all this push for more secure software products. Thank you kindly for the view, and until next time, remember to think, design, and work smart.